I'm John McGee. I work for Wolfram Research in the Technical Services Group. I work remotely out of Southwest Virginia. My talk is about a package for elliptic curves. Well, good morning. Thanks for showing up. Hopefully you'll learn something. I know I did in preparing this. So elliptic curve package for Mathematica. It's going to be introduced at a basic level. One of the real themes, I think, is having a good algorithm is a lot better than having a million computers. So we'll see as that goes through. So a little background. What's an elliptic curve? An elliptic curve over a field is the zero set of a non-singular cubic polynomial in two variables, at least in the basic sense, as the equation or the form indicates there, where the degree is 3. It's also an algebraic variety. Typically anyway. The general form of a cubic of degree 3 is shown there, but for an appropriate change of variables over fields that don't have characteristic 2 or 3, because essentially you have to divide by 2 or 3 to do the change of variables, you get this simplified, called the short Weierstrass or just Weierstrass form, and the condition for not being singular, meaning at least over the reals, over R2 means no kinks and no crossovers, right? Differentiable everywhere. So some general curves, just briefly. They can have all kinds of shapes when you use the general equation, all kinds of crazy, interesting shapes and forms. What makes them interesting? Why are they important? Well, in my examination of these objects, it turns out they lie at the intersection of a lot of interesting branches of mathematics. Number theory, geometry, both in the high school sense and in the real sense. Group theory, commutative ring theory, complex variables, and beyond. So they really act as a focal point of deep study. They're used as a tool in algebraic number theory, the congruent number problem. That is, is the number such that it's the area, a rational number that's the area of a triangle with rational sides can be worked with elliptic curves. And famously, Fermat's last theorem was proven. Andrew Wiles and Taylor and many others using elliptic curves. They're used practically in computational number theory, such as the elliptic curve integer factorization that's found in the Great Internet Prime Search. And also there's an ECM in Wolfram as part of Wolfram's tools for factoring large composites. And in cryptography, those are a couple of techniques that are used for employing elliptic curves for cryptography, with the main advantage that elliptic curves, because the discrete log problem is harder there than it is in other places, you can use smaller fields. And so here's the idea to start. We can create a geometric arithmetic of points by defining the sum of points as the reflection about the axis of symmetry of the third point of intersection. And so here's a little example. And we need the reflection, not just the third point of intersection of a line between 2 points in order to get an identity and inverses, as we'll see. So we can change these around. And then what happens when the points are the same? Well, we can use the tangent line. And this gives us a nice arithmetic ability to add points on the curve. Algebraically, that has a form where the slope lambda is either rise over run simple formula, or the implicit differentiation of the Weierstrass form will give you that. And then you can find the third point of intersection nicely without heavy algebra, the following way. I think this is live. Yeah, so if you intersect the line with the curve, you can replace y squared with the right-hand side of the lines term squared. And has this been run? No, it hasn't been run, so let me do that. resolution change. Okay, sorry. Okay. So letting the computer do the algebra simply, I can find the equation that matches those two. It's a cubic in x, and then equate that to the factored form where I already know two solutions, the 2 points I started with. So the third point must be the third factor, and then we can let the algebra system equate the coefficients of x squared, which is known quantities on the left side, lambda squared, and we know two of the three factors on the other side, so we get the nice expression. And then the point lies on a line, so the y-coordinate is simple. But an interesting thing about this algebra is that the resulting coordinates of the third point, or the reflected third point, are rational functions of the input coordinates. Means integers in, rationals out, rationals in, rationals out. Any field element in, and I stay in that same field when I do the point arithmetic, and that's an important attribute of this arithmetic. But we don't have a group yet, and to get the group, we have to go into projective space. We can think of projective space P2 as the set of all directions or lines in R3 that pass through the origin. More technically, it's the equivalence class of all triples where two triples are equivalent if one is a multiple of the other. And we have a copy of R2 in there simply considering the points that the equivalence class was z equals 1, but there's extra points that aren't in R2. We call those the points of infinity, and they all have z equals 0 as their coordinates. We can transform our original Weierstrass elliptic curve into projective form by multiplying through by z cubed, as shown there, the standard technique, and it gives us a homogeneous polynomial in the three variables, so each term is of total degree 3. And homogeneous polynomials have the characteristic that if xyz is a solution, then so is kxyz, because we get a factor of k cubed in each of the terms. So when z equals 1, we plug z equals 1, we get the original curve back. But when z equals 0, we get a new solution, and this is the magic. So when z is 0, the homogeneous equation reduces to x cubed equals 0, and that gives me a new triple root. That's the point in projective space, since x is forced to 0, but y is free, so any value of y works, and that corresponds to a vertical line. Projective space took me a little while to figure out how to represent this nicely, but there's a picture that I like. The upper plane is at z equals 0, and every point on that plane corresponds to one of the points in projective space. The line through the origin, but not including it, are the equivalence classes. But as we get further and further out at z equals 1, those lines become almost parallel to the plane, but they never get there. So the extra points in projective space are the ones at z equals 0, representing the directions in the base plane. So it turns out with this extra point that satisfies the homogeneous equation, we get a nice group law. P plus Q using the addition formulas above, the algebraic addition formulas. Now P plus that infinity point gives me P back, and I also get inverses in a similar way. It's commutative because geometrically, if I add 2 points, put a line between 2 points, it doesn't matter which one I pick first. The third point's always the same. And associativity is a little hard to prove. It's murder algebraically to prove, but using a little bit higher mathematics, it's not too hard, that this is also associative. So you get an algebraic group out of these points. And just an illustration of why the point at infinity works. If I take P and add that point at infinity, what I do is take the third point of intersection, which is this guy, and reflect it back, and I end up where I started at the original P. And inverses work the same way. If I take P and negative P and add them, the third point of intersection is the point at infinity, and it's its own additive inverse. So we get a nice group law. Okay, the order of a point. basic algebra, a point has finite order n if n times p, which we're in an abelian group. So np, we're really working in the z-module representation. That is, np is really p plus p plus p n times. If I get the identity and n is the smallest one, then that's the order of the point. And we can compute np efficiently using the binary expansion of the integer multiple. I expand it in the powers of 2, and then np is just, well, the product through distributing p across that. And I only have to do the addition for the non-zero binary digits, bi. And so that gives me a pretty efficient order log n additions of the operation. Another interesting subset to examine, if I look at points only of order n or divisors of n, they're denoted this way, so that's all points of order dividing n. And a fairly deep theorem says that that's isomorphic to 2 copies of Zn, integers mod n. But to find all the points, there's n squared of those points, we have to look into the algebraic closure. So not all of them are in the base field. So how do we find the order of a point? Well, if it's a small curve, we can find the order directly by using Shank's baby step. Well, we can find it directly by just computing NP. Otherwise, Shank's baby step, giant step is effective. What we do is, given a point, we compute another point, that's the field power plus 1 times the point, and then look for a match between 2 lists, a list of multiples of p and a list of q plus k times mp, where m is approximately the square root of the field power. And we get a match between those 2 lists pretty quickly because of the birthday paradox, essentially, probabilistically, although the algorithm is deterministic in that it searches far enough to guarantee finding a solution eventually. So if we find that match, that is jp is that, we can collect terms in p, and we know that this resulting number m must be a divisor of the actual point order. It's an effective algorithm, but it's not so good in that it's not polynomial. And it took me a while to get my head around this. Q to the 1/4 or p to the 1/4 doesn't sound so bad, but imagine it takes 10 microseconds to add 2 points of 10 digits. Then if you go to 10 to the 100th power, or 10 to the 110th power, multiplying by 10 to the 100th, then 1/4, the 4th root of that would be a 25-digit number. That would be the multiple of the time it takes. So microseconds go to seconds with 10 to the 6th, go to years with another 10 to the 6th, so you're still left with a number that's 10 to the 13th digits or so long, multiplied by, in years, of how long it would take to go the step. So this is not feasible for large Q. One of my adventures, I attempted to parallelize Shank's algorithm, and it revealed something interesting about Mathematica, actually. It's always bad to parallelize something where you have to move a lot of data around between the cores. To build up the JP list, essentially adding the point to itself over and over again, that list usually is about a million points in it in a real problem. We need to, if we save only the x coordinates and make an association that maps the x coordinate to the actual multiplier, then we can do the other search for the QP, Q plus KNP this way. Essentially what it's doing is doing constant lookups in that association. I tried to parallelize this, but I realized that dividing that list into 4 pieces over 4 processors makes the list 1/4 the length, which has no effect on the lookup time, because the lookup time in the association is almost constant time, almost independent of size. So the overhead of trying to parallelize this didn't really help much, but an interesting lesson. A third case where, well, our associations are so efficient that making them shorter doesn't help. Okay, so we're after not only point order, but the size of the group, which is critical for both theoretical studies and for cryptography. It turns out you can get the right algorithm if you're on a particular elliptic curve. This is a theorem that Gauss proved. And in this simple case, we can compute the order directly using essentially a formula that has two cases. Here's an example of this for the two cases. A curve of order 31, that's 31 is 1 mod p, so we get some extra points on that curve. But the nice thing, it's a direct formula for the number of points without actually doing extra work. It's straightforward. In the more general case, it's a lot harder. So a simple approach to group order, a couple of basic theorems of algebra. The order of a point must divide the order of the group, Lagrange. And a beautiful theorem of Haas bounds what the order of the elliptic curve group is, that is the points with coordinates in the base field, to within plus or minus 2 square roots of the field size. So if we know the order of a set of points and the least common multiple is in that range, then we have the group order. A couple of notes though. If I find a single point with an order bigger than that size, then there can only be one multiple of it within the Haas's range. So it must be, that multiple of it must be the group order. And an interesting observation that if this field contains one or more points with order that big, then a randomly chosen point is likely to have a large order because the size of this entire collection, including the points in infinity, goes as n squared. So I did a little experiment using a parallel version of group order. So here's a reasonably sized curve, 30 digits or something. And I chose 1,000 points on the curve and did their point orders by parallelizing the algorithm. And you can see that there is a nice quadratic shape to these, but every single one of these points is large enough to uniquely determine the group order. So if the determination of group order was efficient, this would be a great solution. You pick a point at random, the multiple of its order is unique in the Haas bounds, so you're done. But unfortunately, the baby step, giant step algorithm grows too fast. So briefly, René Schooff's brilliant invention was to first construct a set of, use a set of polynomials that are 0 precisely on points of order n, or points dividing n, the division polynomials. Their degree grows quadratically, but we can keep them simple and reduce by modding both over the curve, that is replacing all even powers of y with an even power of x. And also, of course, modding by the field that we're in. These polynomials can be used to construct an explicit polynomial, rational function actually, formula for a multiple of a point. And by the way they're built, the y's will never be there. Y's only exist in odd powers of these polynomials. But it's not a good way to compute NP. What it's used for is Schooff's algorithm. Using Haas's theorem, what Schooff does is select a set of small primes whose product is at least the total width of the Haas bounds. And then for each of these primes, determine the missing element in the formula for the group size, mod those small primes using polynomial arithmetic where my multiples of points in the basic formulas are replaced with the division polynomial-based formula. Once I know t mod all these small primes, I can get the actual full t back using the Chinese remainder theorem. The problem is the size of these polynomials grows as n squared, and so it dies at around 80 or 90 digit numbers. The solution provided by Nomelkes and Atkins was to find special primes so that there's divisors of the division polynomials that grow linearly with the prime size. And this gives nice performance, order log to the 6th power of n. So going back to the multiply by 100 digit number, assuming this is base 10, that's 100, and you get 100 to the 6th, which is only 12 million, 12 digits multiple. So your 1 microsecond becomes a couple of hours, maybe, instead of thousands and thousands of years. Okay, and just a quick example of running Scof's algorithm. Here's some time passes on a curve. We get all of these modular relationships for the missing element. And we use the Chinese remainder theorem to put them back together. And we get the group size as Q or P plus 1, plus or minus that guy, plus in this case. And this ran in 5,899 seconds, about 2 hours. Okay, this is related. One of the reasons you care about group order and point order is because the discrete log problem, given a point and some unknown multiple of it, find the k. If the group order is bad, like a prime or a smooth number, which is the product of a bunch of small prime factors, then there are attacks that make the discrete log problem used in cryptography too easy to solve. So where are we? We have a package that does basic arithmetic. I've spent some time struggling with moving old, large notebook code into package form. But where I'd like to go with this is into elliptic curves over C, the Weyl pairing. I've done some work mathematically, but not yet algorithmically. I've been a little busy with other things. So that's where we are so far. The package will be available. Interestingly, all the work that I've been trying to do was done by Crandall and Pomerantz, a nice book with Mathematica code called PrimeKit, which no longer exists on the internet anywhere. I suspect one of two things. It was really bad Mathematica code and Stephen had it pulled, or it was really, really good Mathematica code and the NSA owns it. Thank you. Okay. Questions, I guess? No, it's pulled from there too. So. No, seriously. Yeah. It looks like it was very formally scrubbed. There's lots of websites that claim they have it, but it's not there. So anyway. PrimeKit, yes. Yeah. Yeah.
But is it available in Mathematica?
It's not even available internally, as near as I can tell. So, and I just discovered this on Friday, so I'm not sure where it went. But it would have been nice to have that code. Okay, any other questions? All right, thank you.